Everyone. Welcome back to another digital SAT math lesson. And today we're going to be talking about something very cool. It's linear inequalities. And some of the topics we'll be covering would be solving, graphing, compound inequalities, and solving of systems of inequalities. So without any further ado, let's talk about how we can solve inequalities. So the first basic principle is you treat them just like equations. So here, 3x plus 7 is greater than 16. Simply collect the like terms, negative 3x is greater than 9, and then we divide by our prefactor of negative 3. But one critical thing you want to always remember is whenever you're dividing by a prefactor that's negative, so in that case that's negative 3, you have to flip the sign. So here you had negative 3x is greater than 9. You simply divide by negative 3 and you end up with x on this side, negative 3 on that side, but you flip the sign from greater than to less than. You can think about it in terms of just by plugging in numbers essentially. For example, negative 3 times negative 4, that gives you plus 12, which is greater than 9. So in this case, negative 4 is actually less than negative 3, just because we're going the other way when we're dealing with negative numbers. The other thing to remember would be when you're taking reciprocals. For example, if 1 over x is greater than 5, then we say x is less than 1 over 5. And this is actually for a very simple reason that if you actually start here, forget about this for a second. And if you just multiply both sides first by x, so you end up with 1 is greater than 5x, and then you divide both sides by the prefactor of 5, you end up with 1 is greater than 1 over 5 is rather greater than x. So then if you actually write down x on the left hand side, you end up with x is greater than 1 over 5. So you have this flipped sign here. Next, we'll talk about compound inequalities. So this is like there's two kinds of compound inequalities. The first one is an and inequality or an intersection. For example, negative 2 is less than 3x plus 1, which is less than or equal to 10. So for this, we're solving two inequalities. One is negative 2 is less than 3x plus 1, and 3x plus 1 is then less than 10. So you can simply solve this. There's a graphical way to solve this, of course. You can always plug it into Desmos and you can get your answer straight from Desmos. You can also work it out manually. For example, if you solve this one, you get negative 3 is less than um, 3x, so you end up with x must be greater than negative 1. And the other condition we get from this inequality, which gives us 3x is less than or equal to 9. Therefore, x must be less than or equal to 3. So that gives us our final answer of x being greater than negative 1 and less than or equal to 3. And you can also graph this pretty easily. Just just go ahead, draw your x and y axes, draw the line 3x plus 1, and then right here, negative 2, 10, and here you can always identify the points on the line that align with these values. And then simply this region of x values right here, you can shade it. That would be your correct answer. You can also have a union or an OR inequality where at least one condition must be true. So it's x less than negative 3 or x is greater than 3. For that, you can, again, if that's your condition, then the way you would graph it is you draw x is equal to 3, x is equal to 3, this is x is equal to negative 3, and then this region and this region, those are your solutions. Whereas over here, when you have an and inequality, it's the region between these. That's your solution. So for graphing, the simple procedure that we just saw, it's really 4 steps. or rather three steps actually. The first step is you graph the boundary line y is equal to mx plus b. So when we had 3x plus 1, we graph the line 3x plus 1, and then you draw some dashed lines for greater than or less than. So those are our strict inequalities. So for example, when we had negative, it's greater than -1 and less than or equal to plus 3. When you have -1 right here, you draw a dashed line because this line right here, -1 itself doesn't satisfy our condition. Like if you plug in -1 here, you get -1 times 3, -3 plus 1, -2, which is not greater than -2. It's equal to -2. So we draw a dashed line to just indicate that. And then over here, you have your plus 3. And since this is actually less than or equal to, in this case, we draw a solid line because 3 also satisfies the condition. And then simply you can shade your region if it's an and inequality, and if it's an or inequality, then you shade the region outside of those lines. Let's look at a practice question really quick. Valentina bought two containers of beads. First container had 30% red, the second one had 70% red. Together, at least 400 red beads there were, I suppose. Which inequality should we pick? So you can simply try formulating the equations or rather inequalities first. So think about the situation. The first one has 30% red, the second one has 70% red. So we can simply assign them variables. The first one we can call it x, the second one we can call y, and then we say that when you take the 30% red, rather, so we know 30% times the first one, so the total number of beads in the first one, and then 70% times the total number of beads in the second one, we know combined there were more than 400. So we just add them up and we say 0.3x plus 0.7y must be greater than or equal to 400. So at least that would mean greater than or equal to. So sometimes there are words that you want to be mindful of. So if instead of at least they said together they had more than 400 beads, then we wouldn't say it's greater than or equal to, we would say it's greater than 400. It's strictly greater than 400. So the golden rules to remember would be always flip the inequality sign when you're multiplying or dividing by a negative number or taking a reciprocal. And for systems, a point has to satisfy all inequalities to be in the solution region. So whenever you have a system of multiple inequalities, it has to satisfy both of the inequalities. Or if it's an either or case, in that case, you must graph both regions. So there you go. As always, keep practicing, keep improving, and thank you for joining this lesson. I'll see you in the next one.